Okay, continuing on with example number 2. The function represented by the thin line is a transformation of the function represented by the thick line. Write the equation of the transform function, state the domain and range, and state any invariant points. So it gets a little bit tricky when you're working with a straight line to determine the stretch factor, whether it's horizontal or vertical. So what can help you is identifying your invariant points first. This can be an aid in identifying what type of stretch is occurring. So we can look at this and we can see clearly the y-intercept is our invariant point, which occurs at 0, 1. So we'll just identify that because that's what one of the things we're asked to find. And so because this point has not changed, that tells me that if there is a vertical stretch on this, the y-intercept would have changed. Because this has not changed, it has to have a horizontal, okay? And so a horizontal stretch would mean our horizontal values are changing, and we can clearly see the x-intercepts have changed here. So that tells me that it is a horizontal stretch by a factor of, and then now we're going to look at how this has changed. This has changed from a distance of 1 to 3, so really that stretch factor is going to be a factor of 3. What would be our new equation? Okay, so our new equation for this function would be is equal to, well, when I apply my horizontal stretch factor to my function, I want to apply it directly to my x value, and I'm going to replace x with 1/3 x and then add 1. So remember, with horizontal stretches, we're going to describe the stretch as 3, but when we put that value into our equation, we need to reciprocate that value. And then quickly, the domain of is obviously going to be all real numbers, pretty straightforward, and our range is going to be the same. Okay, all right, moving on to B. When we look at something like this, I first want to try to identify our invariant points, and we can clearly see that because neither of these graphs actually cross the x-axis and our intercept has changed, that in this case there's going to be no invariant points. And because our y-intercept has changed, this clearly tells me that a vertical stretch has occurred by a factor of 4. The 2 becomes an 8, so it's been vertically stretched by a factor of 4. All right, so what's our new equation going to look like? So if we're applying a vertical stretch, we want to apply that vertical stretch to the entire function. So I'm going to multiply my entire by 4. Vertical, we do not reciprocate this value. We leave it the same. And I need to apply that stretch to the entire function. So really, we could clean this up a little bit by multiplying my 4 times my 2 to give me 8 would be my equation. Okay, domain and range. My domain, fairly straightforward. It looks like x is going to be all real numbers. It's never ending. And the range should be anything greater than 0, but not equal to it, and less than or equal to 8. All right. Okay, moving on to example number 3. This can be a little tricky when you start to ask for transformations of just basic parabola. So we're given the function g of x. This is a function of f of x, so we've went from here to here. And so many students could look at this, and 2 different students could see 2 different things. Okay, you just have to be aware that different stretches. So when I look at this, I might look at this function and I notice that the vertex has not changed, which is the origin. So technically this invariant point isn't going to help me determine whether it's a horizontal or vertical stretch, because both my x and y values are 0 here, so this doesn't aid me. So then what I have to start doing is actually looking at specific points on the graph. So one student might look at this and say, well, us at these 2 points, my y value is not changing and my x value did. Same thing down here. If I look at these 2 points, my y value did not change, but my x values did. So when we look at this, I can clearly see that my original x coordinate went from a 4 to a 2 here, or a 2 to a 1. So this tells me that there has been a horizontal stretch, just use HS for short, by a factor of 1/2. Distance is now 1/2 of what it originally was. Okay? So when we go to write our equation, I need to apply this stretch factor just to my x coordinates, but remember, as a horizontal stretch, we want to apply the reciprocal value. So I'm going to apply a 2, replace x with a 2x, and then I need to square that entire function. So if we expand this, what do we have x function? Well, 2 squared gives me 4x squared. So that would be our simplified equation. So another student might come along and they might look at this completely different, and they might see, well, if I look vertically between these 2 points and these, they might say, well, my x coordinates are not changing and it's my y coordinates that are. So someone might think that this could be also a vertical stretch by a factor of 4. So originally this point is 1, it's now at 4. This is at 4, it's now at 16. So these are 4 times the distance as it once was. So when I go to write my equation, I now need to apply that stretch factor to the entire function. And my entire function is simply x squared. And so what ends up happening, we get the exact same equations, whether you see it as a horizontal stretch or a vertical stretch. So we actually get the same result by seeing 2 different possible stretches. Okay, so this can occur occasionally and you just need to be aware of it. All right, moving on to example 4. The graph of f of x is equal to x squared minus 2x, x cubed minus 2x squared minus 5x plus 6 is shown cubic function. I've identified our x-intercepts. I've also identified our y-intercepts. There's just key time. It says write the equation which would represent y equals f of negative 1/3 x. Well, negative 1/3 x means this is what I physically want to replace with every x value in my equation. So my mean, negative 1/3 x all cubed minus 2, negative 1/3 x all squared minus 5 times negative 1/3 x plus 6. So simply give me a negative 1 over 27 x cubed minus negative 1/3 squared would be a positive 1/9 times a negative 2/9, so minus 2/9 x squared. Negative times a negative becomes a plus 5 x plus 6. So now we just want to talk about what this does to specific values on the graph. So describe how the number negative 1/3 in the function in this transformation affects the general stretch of y equals f of x. So now we're all combining a stretch factor with reflection. So because this is being applied just to x, this tells me it's a horizontal stretch by a factor of 3. We want to reciprocate that value. Reflection in the y-axis. So the negative is applied to the x, so it's like a horizontal movement. So we're reflecting in the y-axis. How does it affect the x-intercepts? Well, originally our x-intercepts were negative 0 and 3, 0. So when we start to combining transformations, we want to start thinking about the proper order of things, and we always need to apply just a general rule to apply the stretch first. So what I'm going to do is I'm going to stretch each of these points by a factor of 3 to begin. So the negative 2, 0 becomes a negative 6, 0. 1, 0 becomes 3, 0. And 3, 0 becomes a 9, 0. So this is after the stretch. Next, so now I'm going to reflect each of these points in the y-axis. So the 6, 0 is going to become positive 6, 0. 3, 0 is going to become negative 3, 0. And 9, 0 is going to become negative 9, 0. So this is after the reflection. So we generally want to do the stretch first, reflection second. Okay, and then lastly, how does it affect the y-intercept? Well, in this case, the y-intercept will not change. Horizontal stretch isn't going to change that point, and if we reflect it in this line, it's not going to affect that point either. So 0, 6 is actually the... Okay, and that is stretches.